Chapter 7: Cathode Rays and Cathode Ray Tube. When a metal is heated to very high temperature, electrons may be emitted from its surface, and this is because the electrons gain enough energy to enable them to break loose from the force of attraction of the nuclei. The process of emission of electrons due to heat energy is referred to as thermionic emission. What we need is to produce electrons that move in a vacuum. We have a vacuum tube inside of which is a highly negative cathode and a highly positive anode. They are separated by a vacuum and connected to a high voltage DC supply. If the cathode is heated, electrons of the metal atom are excited and move a little away from the nuclei and then back. So when the DC supply is switched on, the negative electrons are repelled from the negative cathode and attracted to the positive anode traveling through the vacuum. So we get a beam of electrons traveling through the vacuum. The high voltage drives a current through the heater filament, which in turn hits the cathode to release the electrons. Production of cathode rays. Cathode rays are streams of electrons from the cathode to anode produced by thermionic emission. Cathode rays are produced in a cathode ray tube. The cathode ray tube is the forerunner of the television tube. It has a glass tube from which air has been evacuated. When the twin metal plates are connected to a high voltage source, the negatively charged plate called the cathode emits electrons which are drawn to the positively charged plate called the anode, where they pass through a hole and continue traveling to the other end of the tube. When they strike this specially coated surface, the cathode rays produce a strong fluorescence or bright light. Properties of cathode rays. Cathode rays travel in straight lines, and when an opaque object is placed on their path, a shadow is cast on the screen. Cathode rays cause certain materials to fluoresce, such as zinc sulfide or phosphor. When an electric field is applied across the cathode ray tube, the rays are attracted to the positive plate. They are therefore negatively charged. These charged particles are electrons. The moving charges behave like tiny magnets and interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the field is reversed, the beam of electrons is deflected in the opposite direction. Cathode ray oscilloscope. Some modifications are made to the cathode ray tube to make the cathode ray oscilloscope, CRO. The CRO is built up of three main parts. The first part, which looks like the cathode ray tube but with a few modifications, is named as the electron gun. This part produces electrons by means of thermionic emission. The second part is the deflection system, and it causes the deviation of the electrons from its normal straight path according to the voltage applied to the plates. It consists of the Y plates, which are responsible for deflecting the beam of electrons vertically up and down. The other two plates are named X plates and are responsible for deflecting the beam horizontally, left and right across the screen. The voltage of the X plates is controlled by a button on the interface. This button is called the time base. The third part is the fluorescent screen. This screen is plated from inside with a layer of a substance that is sensitive to electrons. It gives a bright spot on the position where beams of electrons fall. The electron gun. The purpose of the gun is to supply electrons, accelerate them towards the screen and focus the beam to a point on the screen. It consists of a heated cathode, a grid to control the rate of electron flow, and anodes to accelerate and focus the electron beam. Each of the parts is maintained at a DC potential from an EHT source and a potential divider. The cathode is coated with oxides of thorium and strontium, preferred for the yellow work function. The anodes consist of cylinders and discs maintained at a high positive potential relative to the cathode. They therefore attract the emitted electrons and eventually direct them towards the screen. Focusing the beam. Anodes A2 and A1 are at different potentials, that of A1 being higher. There is therefore an electric field between them. The direction of this field is such as to converge the diverging beams from the cathode as it leaves the aperture of anode A1. The greater the potential difference between anodes A1 and 2, the greater the electric field intensity and therefore the greater the degree of focusing. The grid. The cathode is surrounded by a hollow cylinder, the grid, which has a small hole at the end. The cylinder is at a small negative potential relative to the cathode. It is used to control the intensity of the beam in that when the grid is made less negative, more electrons cross over, and when made more negative, the number of electrons crossing over the screen is cut down. The grid therefore controls the intensity of the beam and hence the brightness of the spot on the screen. The deflection system. Vertical deflection. When the beam passes between uncharged horizontal plates, it strikes the screen at A. The beam is therefore not deflected. When the switch is closed, the plates become charged and the beam is attracted towards the positive plate Y1. It is therefore deflected to hit the screen at B. If the polarity of the plates is reversed, the spot will shift to C through A. If the reversals of the polarity are sustained, the spot will shift from B to C and back at a frequency of the reversals. With an alternating voltage, the spot moves up and down in accordance with the instantaneous voltage at the frequency of the AC. If the frequency is high enough, a vertical line is observed rather than a moving spot due to persistence of vision. Since the plates cause deflection in vertical direction, they are called Y plates. Horizontal deflection. When the plates are arranged vertically, the beam of electrons is deflected horizontally across the screen from point M to N and back, as the polarities are reversed. Since the deflection is horizontal, the plates are referred to as X plates. In the CRO, a voltage varying is applied to the X plates from a special circuit known as the time base. The sweep of the spot across the screen can be adjusted using the time-based control knob, which operates the frequency of the time-based voltage. The higher the frequency, the shorter the time of sweep. If the frequency is now raised, the movement of the spot gives a permanent trace of a horizontal line across the screen. Simultaneous application of the input voltage at the Y plates and time-based voltage leads to the movement of the spot on the screen in 2 dimensions, producing 2-dimensional image of input voltage on the screen. How do we determine the frequency of an AC signal? The signal is fed into the Y plates of a CRO with the time base on. The time-based control is then adjusted to give 1 or more cycles of the input signal on the screen. The time t of the signal is then determined by relating the trace of the signal on the screen with the time-based setting. Frequency f can then be calculated as f is equal to 1 over t. For example, if we take this graph and the time-based control set at 10 milliseconds per division, we can determine the frequency of the AC signal on the screen. Time-based setting is given as 10 milliseconds per division. The number of cycles shown here is 1. Number of divisions covered by 1 cycle is 8. So period t is equal to 8 times 10, which is equal to 80 milliseconds. 80 milliseconds divided by 1000 to give seconds, we get 8.0 times 10 to power negative 2. Frequency is 1 over t, and if we divide that, we get 12.5 Hertz. Another example. This figure shows the trace on the screen of an AC signal connected to the Y plates of a CRO with time base on. Given that the time base control is 5 milliseconds per division and the Y gain is at 100 volts per division, determine A. the frequency of the AC signal, and B. the peak voltage of the input signal. Electronic beams so they can sweep across the entire screen and create the picture you see. In our solution, time-based control is 5 milliseconds per division. Number of divisions covered is 8. So the total time is 8 times 5, which gives us 40 milliseconds. Total number of cycles is 2. So time per cycle, that is periodic time t, is given by 40 over 2, which gives us 20 milliseconds. Frequency is 1 over t, 20 milliseconds divided by 1000 to get seconds, we get 2.0 times 10 to the power of negative. 1 over that gives us 50 Hertz. Tool with holes inside it helps to keep the electron beams aligned exactly with the phosphors. This is called. For part B, Y gain is given as 100 volts per division. Deflection is equal to 3 divisions from 0 level. Peak voltage is equal to Y gain times the number of divisions, which is equal to 100 times 3, and that gives us 300 volts. The CRT monitor screen. Signals from a computer video card are loaded into 3 electron guns at the base of the monitor. There is 1 gun for each of the primary colors, red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen. These guns shoot powerful beams of electrons towards the face of the monitor. The beams pass through the deflection yoke, which induces magnetism to bend the electronic beams so that they can sweep across the entire screen and create the picture that you see. When the beam hits the monitor, special chemicals of phosphor painted on the inside of the monitor are made by the beams to glow either red, blue or green, depending on the type of phosphor. The stronger the beam, the brighter the phosphor glow. A sheet of metal with holes inside it helps to keep the electron beams aligned exactly with the phosphors. This is called a shadow mask. The beams sweep across the entire screen 60 times per second, so quickly that you are unaware of the firing process. Instead, your screen appears as a steady continuous image.
By the 1890s, things really started to hot up. In those times, guys like William Crookes, various other experimenters, all started playing with this new phenomenon of high voltage using a device called a Ruhmkorff coil and passing this high voltage through tubes that the air had been exhausted from. So in other words, they had removed the air from these tubes and they tried to see what would happen if very high voltages were passed through the slot. Now, there is our cathode ray. You can see the ray appearing across the tube. This is the sort of thing that fascinated the scientists of those days. Now, this is very interesting because this led to all sorts of things. And of course, if you continue to experiment as they were doing, what would happen? Discoveries are bound to be made. And this, of course, led not only to the discovery of the electron, but also the discovery of something that I'm sure a lot of us have had dealings with in one way or another, the discovery of X-rays.